this video we're going to implement simple linear regression in R. In the previous video I already gave you an overview of the data that I work with in this series of videos. Just to give you a reminder, you get a visualization here. So I'm looking at time series data from Fred.com. I'm looking at economic indicators such as US GDP, life expectancy, population size, private investments, and research and development. In this plot you see the normalized form of the data. So I normalize the observation values to be assigned to a scale from 0 to 1. And now in this video we use this time series data that we have gathered in one overall data frame to build a first regression model. In this case it's simply a linear regression model. And for simple linear regression you have to decide which ones of your observation values or variables in your study do you want to consider as being your dependent variable. Which ones of your variables do you want to consider as your independent variable. And what we work towards is a linear formula that predicts the dependent variable as a linear function of the independent variable. So you have some constant, or you have some coefficient multiplied with the independent variable plus some constant. That's then your prediction for the dependent variable. In this case we use US population size as being the dependent variable, and we use life expectancy at birth measured in years as the independent variable. First thing I need to do, I need to split my data into a training and a test set. If you want to see in detail how I do it and have some more time to look at the code, please click the link in the video description. You can also copy paste the code into RStudio and try to play yourself with the data and the functions, and also with the documentation available in CRun and RStudio. But this is the first step you need to do. Split the overall data into a training and a test set. And then you start by training your model on the training set. For simple linear regression you can use the default function available in R called LM. It has a formula parameter to which you assign as a first argument the dependent variable, and then as a second argument the independent variable. And then you assign to the data parameter your data set that contains the dependent and independent variable in columns. And in this case it's of course the training set, because we train our model on the training set. This generates a predictor object, which is now my linear regression model object. I can print a summary of that object, giving me an overview of, for example, the coefficients of the model. So this is basically the formula that describes your prediction for the dependent variable based on the training set. You can also see here the p-values of the parameters of the model. They score pretty well. Another important statistic that you see in the summary is adjusted R squared, which should be as close to 1 as possible, and it's certainly pretty close. Just judging by the summary, linear regression and a linear model should describe the dependent variable independence of the independent variable, in this case life expectancy, pretty well. But we need to go further, and we need to look at the data ideally in a visualized form, and we'll need to look at some other aspects as well before we can really judge whether a linear model is the best model or whether we should continue our search for a better model that describes the relationship in our data. The first thing I do here is I visualize the test set. Those are the black dots here. You see on the x-axis we have US life expectancy, and on the y-axis we have US population size. And the red line here, that's our prediction. So that is the prediction model that we generated using the training set and using the LM function. And you can see there's a systematic deviation. In the first section you have positive residuals, so you have basically an under prediction. In the middle section you have an over prediction, and here in the last section you have again an under prediction, so you have again positive residuals. And this is something that seems to be dependent, or this seems to be systematic across the independent variable. So the residuals are somewhat related to the independent variable, which is not good. I mean, when we do linear regression, we don't want this to happen. And if we want to assess the quality of a model. This is certainly one argument against using the linear model. Another thing I look at is using the predictor object. So that's my linear regression object that I generated using the LM function. I can access the residuals and visualize this in a histogram. Ideally, what we want to see is a symmetric distribution around 0. You can judge for yourself if you think this is ideal or not. I mean, it definitely doesn't look like a normal distribution curve. It seems there's some kind of a bias towards positive residuals. Again, not 100% perfect. In this plot, I visualize the residuals that I again access from a predictor object, independence of the independent variable. So this is also what I briefly went about when talking about the other plot. Yeah, and as I previously said, you have some systematic behavior, some systematic error. The higher my independent variable, so when the life expectancy goes over 74, I have a positive trend in my model residuals, and before that I had like a negative trend. Or you could say it another way. In this section again, I have positive residuals. Then in the middle of this plot, I have negative residuals, and then again positive residuals. So systematic behavior. There's some kind of dependence of the residuals and towards the independent variable of a prediction or of our regression analysis, and that's certainly not the ideal case. A QQ norm plot is another thing I do, and what you want to do here is. Or what the QQ norm function does is gives you a plot and shows you the distribution of the quartiles in your data. Ideally, or in ideal case, when we have a very good prediction model that fits the data very well, then you would have the points in your data or the residuals of your prediction. They would lie on a straight line from corner to corner. In this case, we don't really have one perfectly straight line. It's somewhat arranged on a what you could say looks somewhat like a line, but it's not a perfect line. And yeah, the point is clear. We have some kind of systematic deviation from linear prediction. The overall model summary was pretty good, but we have somewhat a dependence of the model residuals on the independent variable, which is not ideal. But nevertheless, I continue by looking at the test set. So we now looked at the model performance and how the model was trained on the training set, how the model itself fits the training set. Now we look at how the model is able to predict our test set. So now we use the test data frame. We generate predictions for our dependent variable, which is the US population size, using the life expectancy values from our test set. And those are basically values that the model had previously not known, since the model was trained only on the training test set, the training data set. So when I visualize the actual observation values and the linear model predictions here, I see how the model performs with regards to the test set. And we get pretty much the same picture as when looking at the model fit in case of the training set, that I have a systematic error. I have under prediction in this first section, over prediction in the middle section, under prediction again when it comes to the end of the plot. So overall, I would say there's a clearly analysis shows there's clearly some kind of linear or some kind of positive relationship between the independent variable and the dependent variable in our analysis here. This also makes sense theoretically and was basically our assumption or our basic hypothesis. The question is, however, whether there's a better model, because we can see that there is some kind of deviation between the linear model and the actual observation values, and especially we saw that the residuals of the regression were dependent on the independent variable. And that's certainly something that is not ideal, and therefore in the next videos we are going to look at a couple of other regression models to see how they behave and how they fit the data.